So let's start with today's lecture. We were studying this slide set number 7. I will just continue with the same thing and let's see where we were and what we were doing. Okay, so this is that concept of eigenfunction and eigenvalue, and we introduced eigenfunction and eigenvalue. And as I mentioned, this term function or signal should not confuse you, it's one and the same thing. Example I gave you was that of a cosine, let's say cosine t. For us, it's a signal. For, let's say, mathematician, it's a function. So if we have an eigen signal or function, the property of that thing is if you give that as an input to a system, the output would be the same eigenfunction multiplied by something, and that something is known as the eigenvalue of that eigenfunction. And we may have multiple of these eigenfunctions. And the beauty of this thing is that if we can express your input signal in terms of sum of scaled eigenfunctions, then the output would be just the same scaling factor with eigenfunction multiplied by their individual eigenvalue. And as I mentioned, one such eigenfunction, a whole set of them, was given to us by a mathematician or scientist by the name of Laplace. He said that a complex exponential of the type e raised to the power of st is an eigenfunction where s is a complex number. S is a complex number. You can just have any complex number here and you will end up getting a complex exponential which will be eigenfunction. And we actually checked that out also, and we saw that if we give that as an input, the output would be the same thing multiplied by its eigenvalue. So the same thing is written here also, that eigenfunction given as an input gives you the same eigenfunction into its eigenvalue. And the main use of the theory would be if we can find out the eigenfunctions and their corresponding eigenvalues. And also if we can somehow decompose your input signal in terms of eigenfunction scaled by some factor, and we should have some method of finding out what that scaling factor would be. Then we can have the proper use of this concept. Then any input signal, we should be able to break it up in terms of eigenfunctions, and we can easily find out the output for those eigenfunctions then. So we would be able to find output for any given input. So this was the whole concept base, and we actually showed that e raised to the power of st is actually a eigenfunction. And how did we show that? We said, well, if we have a system, any LTI system whose input is, let's say, e raised to the power of st, let's see what would be the output. Let's say that x of t was e raised to the power of st. Let's see that what will be the output for any given continuous time system having impulse response h of t. Now we know that output y of t would be convolution of h of t with x of t, and we know property of convolution, you can have any order x first or h first, doesn't matter. And convolution is basically convolution integral minus infinity to infinity h of tau x of t minus tau. And using that, then we just plug in value for x of t, which was e raised to the power of st. So x of t minus tau will become e raised to the power of st minus tau. So here it is, h of tau e raised to the power of st minus tau. And then it can be broken up into two parts. One part will be e raised to the power of st, the other part would be e raised to the power of minus s tau. And as far as e raised to the power of st is concerned, it is a constant, it doesn't have any tau here. We can take it out of your integral, and we end up getting this e raised to the power of st separate multiplied by something, and that something we call that h of s. And this h of s is basically integral of h of tau e raised to the power of minus s tau for the range of tau from minus infinity to infinity. So we can just write h of s for this. So your output became h of s into e raised to power of st. So input was e raised to power of st, output came out to be something which was h of s multiplied by e raised to power of st. So we showed that e raised to power of st is basically an eigenfunction, and the eigenvalue of this eigenfunction is h of s, which is basically this particular term right here. In mathematics, you have seen this. This is nothing but Laplace transform. For those of you good in mathematics, you should already have seen this, that this is same as Laplace transform of h of t. So if you take Laplace transform of h of t, it becomes h of s. This is what it is. So this is basically the whole theory base, and we actually showed that e raised to power of st is an eigenfunction and its eigenvalue is h of s. So, and using this, we actually did a simple example where we took a single system whose differential equation was given to us, and from here we can find out h of t. Just replacing x with delta, it becomes delta t minus 3. So for this system, if we want to, let's say, find out output, if we are given input e raised to power of j omega t, then what do? So if you see this e raised to power of j 2t is basically same thing as e raised to power of st with s equal to j2. So using this, first of all, what we can do is we can find your h of s, and h of s, here we have actually found this h of s. It came out to be e raised to power of minus 3s. So h of s was simply computed using the formula we already know, minus infinity to infinity, h of tau e raised to power of minus s tau d tau. And we just plugged in the value. H of tau was delta tau minus 3 e raised to power of minus s tau d tau. And again, this is what we have right here. Now, if you have the integral in which delta function is there, so it is basically integration of this product for the whole range of tau from minus infinity to infinity. But we know that in this product, this first term that we have, which is the delta term, has value only at tau equal to 3. At all other values of tau from minus infinity to infinity, this will be actually 0. Only at tau equal to 3, this value becomes 1. And at that point, this will become e raised to power of minus 3s. So we can directly write the answer like this. So this is the beauty of having a delta inside integration. If you have a single delta inside integration, you may have multiple other terms multiplied to it, but we can directly write the answer because delta we know has value only at one point. So h of s was computed, and output we know is just output y of t is simply h of s into e raised to power of st. In our case, instead of s we have j2. Instead of s we have j2. So it is h of j2 into e raised to power of j2t. We can just plug in the value of s as j2 here. So if you put s as j2, it becomes e raised to power of minus j6. So answer is simply e raised to power of minus j6 into e raised to power of j2t. So this is the answer that we have right here. This was a simple system. We could have directly found the answer also, because if xt is e raised to power of j2t, x of t minus 3 will be e raised to power of j2t minus 3, and same answer here. For this system, it was very easy to directly find answer. But if we wanted to compute the answer using this concept of eigenfunction and eigenvalue, this could be computed, and the methodology is you have to know h of t. Using h of t, find h of s, and then the output is simply h of s multiplied by e raised to power of st, and we know the value of s here is j2. Just plug in the value, you have your answer. And for the same system where we have found your h of s as this, if we change the input and have a cosine as an input, here we saw that if your x of t or input is cosine, let's say 2t. Then what can we do and how can we find the answer? Again, what we can do is we can break it up in terms of complex exponential. A cosine has complex exponentials which are conjugate of each other, e raised to the power of j2t plus e raised to the power of minus j2t. And if you notice, this has s equal to j2, this has s equal to minus j2. So this one will give you output which is this, e raised to the power of st into h of s, and s here is j2, and we know that h of s or h of s is e raised to the power of e raised to the power of minus 3s. So you can just plug in value s as j2, this becomes here, and same goes here. The output for this thing, same e raised to the power of st, and into h of s, where s is here minus j2, and you get this value right here. So this way we can directly find the answer. And again, then we can combine the exponentials, and once we have two complex exponentials which are conjugate of each other, this is a cosine, we can write it as a cosine. So another further example we did was, instead of one cosine, if you have two cosines, sum together given as an input x of t, then how can we find the answer? The answer there then would be, again, decompose this x of t in terms of complex exponential. So cosine 4t gives this, cosine 7t gives this, and again here we can see that s is j4, s is minus j4, s is j7, s is minus j7, and we know that our h of s is already given here, e raised to the power of minus 3s. So this thing gives this thing, this thing gives this thing, this thing, this and this. So we can have our answer in this particular shape. And then you can just combine all the complex exponentials, and then complex exponential which are conjugate of each other ends up giving us cosine, and we end up getting your answer for y of t. So we can have different inputs, but as long as we can break the input up in terms of complex exponentials, then it is very easy. We can easily find answer for each complex exponentials. So this simple system, how this can be actually solved for different inputs, we have actually shown, and this was what we covered last time. Now coming back to the Fourier theory. So why is Fourier theory important, and where do we use actually Fourier theory? Now before I proceed, let me try asking you guys, if somebody is volunteers, why do you think Fourier theory is important, or what you can say benefits we have from the Fourier theory? Anybody who would like to answer here? Why do you think this Fourier theory is important, or what is the benefit of Fourier theory, or what added thing is given to us by Fourier theory? So all of you have studied Fourier in mathematics. Any volunteer who would like to answer this? Come on, any ideas? Why do you think, what advantage Fourier theory gave us? What we got out of Fourier theory? No volunteer. Okay, so I always advise people to be confident. Just say out whatever you feel like. So this is the time to really clarify your own ideas. Okay, so if there are no volunteers, let me actually try to cover this Fourier theory with you. So Fourier actually helps us in transforming a time domain signal into a frequency domain signal. So this is actually what Fourier helped us in devising. So if you have a time domain signal, here you are seeing a particular time domain signal. So this is basically, I'm sorry, not very good in line drawing. So this is basically your time domain signal. And we have, you can see, changing amplitudes. So if you have time domain signal, we can plot this signal against time and see that how the amplitude is changing. So we engineers, if we plot any function or signal given to us against time, then at any particular instant of time, we can find out what was the magnitude or amplitude of that particular signal. That is all that we can actually see here. But we engineers are interested in finding out more about signal. Specifically, we want to find out the frequency contents present inside the signal. So if signal is given, just looking at it, we cannot actually judge how many frequencies are present in this signal, or what is the range of frequencies present in the signal, what is the maximum frequency, what is the minimum frequency, how many frequencies, and what is the magnitude of each frequency. So these types of things are useful or important for engineers. Just looking at time domain plot doesn't actually tell us that. So if we just take Fourier transform and transform from time domain into frequency domain, this omega is basically frequency domain, then we can plot the same signal in frequency domain where independent variable is omega. And once we plot that, then we can see that what all frequency contents are present. Here we can see we have 2 frequency contents present, and we can see the value of each frequency content. So we know maximum, minimum frequency, or how many frequencies present, and what is the value or magnitude of each frequency content inside that signal. So that is why the Fourier theory is very important for us. And this knowledge actually helps us design systems to filter out either high or low frequency components, whichever are unwanted. We can just remove them. And this can be done if we just know the frequency content. For example, this signal, if you see right here, this is having a particular low frequency content. This changing amplitude is showing us. So let's say if this was the actual signal required, and on top of it we have some noise, some high frequency content riding on this, then we can design a filter which will filter out the high frequency content, and you will be just left with your nice and clean signal present. So these types of things we can do as engineers if we know what all frequencies are present, what are wanted frequency, what are unwanted frequency. So these types of, you can say, analysis are useful and important for engineers, and these are normally done in frequency domain. So we need to actually see the frequency content and accordingly decide which frequencies to keep, which not to keep, which frequency to amplify, which frequency not to amplify. These types of things we can do. So that is what Fourier theory actually enabled us. Now this term transform, I believe I talked about it earlier also. Transform is basically transformation of the independent variable. Here the independent variable was time. Once we transformed it, now the independent variable became omega. So initially it was a function of time, and after the transformation it became function of omega. And what is omega? Omega, we call this as angular frequency. Omega is angular frequency, and this angular frequency, typically we are more used to actual frequency, which is f, and f is the frequency in hertz. This is the frequency that we know of in terms of hertz, or in other words, oscillations per second or cycles per second. So cycles per second is also hertz, the unit is hertz. So angular frequency is just scaled version of the same thing, 2 pi times this frequency. In continuous time, omega is basically 2 pi times f. So whether you plot it against omega or you plot it against f, if you plot it against f, it will be this whole axis gets scaled by 2 pi. So it's one and the same thing, just a scaling factor of 2 pi is there. Okay, so this was basically some details about the Fourier theory. Now, once we take Fourier transform of any time domain signal, let's say x of t, what we end up getting is basically initially we had function of time, because x of t was a time domain signal which was function of time. And once we took Fourier transform of that, we ended up getting xj omega, which will be function of omega. So independent variable got changed. Once independent variable gets changed, that's a transformation. Transformation means going from one domain to other domain. And this term domain, don't be confused with this name. What is this domain? Domain is nothing but the independent variable, this omega or t. So from time domain going to omega domain, or for independent variable t to variable omega. So instead of plotting against time, we can plot against omega. So instead of just seeing that what is happening at every time, we can see what is happening at every omega point. So this is basically what Fourier transform actually does. The other important and beautiful feature of Fourier transform is, if Fourier transform of x of t is xj omega, then Fourier transform of the derivative of x of t, x prime t is actually derivative of x of t, then Fourier transform of this derivative would be the same xj omega multiplied by j omega. This is a very important feature of Fourier transform. If Fourier transform of x of t, if it is xj omega, then if we take Fourier transform of the derivative of x of t, it would be the same xj omega multiplied by j omega. So the derivative is removed and we end up getting a multiplicative factor, j omega. So this is a very important and useful property of Fourier transform. For engineers, one important property was that, well, it helps us in seeing the frequency content. So we can just plot it against frequency and see what all frequency contents are present. This is one importance of Fourier theory. The other importance is we can get rid of the derivatives once we go into the omega domain. The derivative gets removed. And this actually helps us in solving, as we say, differential equation. So let's say if you're given this type of a differential equation, and again, this differential equation may be representing a particular system with a particular property. So this, if we take Fourier transform throughout, then Fourier transform of y of t would be yj omega. Fourier transform of its derivative will be yj omega multiplied by j omega, and two factor gets multiplied. So derivative of y, if you take Fourier transform, it will be the same yj omega multiplied by j omega. And if you take Fourier transform of the second derivative, it will be yj omega multiplied by j omega square. Okay, so j omega square means j omega multiplied by j omega, that j square is actually -1, so minus omega square by j omega. So you see that at the end, we end up getting the whole expression in terms of omega, and the whole derivative thing gets removed. And from this, if we just take yj omega common and eliminate that, we end up getting this particular equation, from where we can take roots and find out values of omega at which the whole expression becomes 0. So this is something which we will see later. But the feature of Fourier transform, that is what was important, that one feature is that it actually transforms from time domain into the frequency domain. The other property of Fourier transform was that it helps us solve differential equation, because once we take Fourier, the differentiation gets removed. So that is the second, you can say, important factor about Fourier transform. Okay, so now let's see that whatever we have seen for eigenfunction and eigenvalues, how does the Fourier thing gets fit in? So these examples actually we did. So some history of Fourier. Fourier actually studied harmonics, and this study he carried out way back in 1700s. Originally, the study of you can say harmonics was carried out by Euler. As I mentioned, we pronounce it as Euler, although it is written as EULER. Okay, so Euler actually studied vibrating strings and found that for a particular length of string, the frequencies that can be present are just multiples of each other. And these multiples of these frequencies are basically what is known as harmonic. And this concept of harmonic was picked up by Fourier and actually used in describing a particular series which is known as the Fourier series. So Fourier described how such a series of harmonics could be applied and showed that a periodic signal can be represented as sum of sinusoids that are not harmonically related. So this is what Fourier actually did. And this concept was actually later on developed and used by engineers, and we are still using the same theory. Okay, and for us, how this Fourier series is important and how the harmonics are important and what are Fourier basis functions, this is what we are going to see. So let me just go on to the whole definitions of the use of this thing. So at the end of the day, Fourier, okay, let me just first finish this slide and then go there. The theory derived for convolution that we have seen earlier used the concept that any input signal can be represented as linear combination of shifted impulses, or in other words, sum of scaled delayed impulses. This was the concept which was used to derive the convolution, that we can have any input signal x of t. Rather, it was basically used for x of n and then further extended to x of t. But the whole concept is that whether you have a discrete time or you have a continuous time, we can, either for continuous time or discrete time, we can actually represent the signal in terms of scaled delayed impulses. Now, we will see that how we can represent any input signal or an input signal in terms of linear combination of Fourier basis functions. And these Fourier basis functions that we are going to use are also eigenfunctions. And these Fourier basis functions or Fourier eigenfunctions are basically purely imaginary exponentials. So this is what we are going to see right now, that how Fourier gave us as eigenfunction, and those eigenfunctions that Fourier gave us can also be used as basis functions or building blocks. And these building blocks can be combined and made into any particular input signal, or in other words, any input signal can be broken up in terms of the basis functions. So this is what we are going to see. So once we express the input signal in terms of Fourier basis functions, we end up getting what is known as continuous time Fourier series. In mathematics, you have already done and studied these Fourier series from pure mathematician's point of view. Here we are going to take a look at the same thing from a different angle. And the basis functions that Fourier gave us are scaled and shifted sinusoid signals, and they can be represented as complex exponentials. So this is what Fourier told us. Okay. The theory started by Fourier actually talks about a periodic signal first. And the theory that Fourier gave us was theory of Fourier series. And this Fourier theory is applicable, initially that he talked about was applicable for periodic signals. And what he said was that if you have a periodic signal, what is a periodic signal? We know that a periodic signal is a signal which repeats itself after a particular time period t. So whatever is the value of x of t, the same will be value for x of t plus any multiple of time period t. So you can have any particular kt or nt here. And t is the time in which the whole periodic thing repeats. And t is also known as the fundamental period or time period. And t is linked with your fundamental frequency f naught by this relationship, that fundamental frequency in terms of what is 1 over t. And fundamental angular frequency is basically 2 pi f naught. So we can just have this thing as 2 pi over t. So the relationship between time period, fundamental frequency, fundamental angular frequency, these are actually shown right here. If t is in seconds, f naught comes out in hertz, and this comes out in terms of radians per second. So units are kind of different, but this is the relationship between time period, fundamental frequency for a particular periodic signal. Now, most commonly known periodic signal is a sinusoid. So we know that cosine is a periodic signal which repeats after a particular time period t. Now similarly, a complex exponential e raised to power of j omega naught t, that is also a periodic signal. It's a complex exponential, but these complex exponential, we know that we can express it in terms of sinusoids. A real part, imaginary part, both are actually sinusoid. So it is also a periodic signal. And this omega naught right here is basically the angular frequency of that signal. And from this omega naught, we can extract your time period or fundamental frequency f naught in terms of hertz. All that can be extracted from this particular multiplicative factor, which is given as omega naught right here. So a sinusoid is a periodic signal. Complex exponential is also a periodic signal. And this complex exponential, this is the one that he gave us as e raised to power of j omega naught t. This is the Fourier eigenfunction also. This is that eigenfunction that Fourier identified. And this eigenfunction that Fourier identified is also a basis function because it can be actually used as building block for periodic signal. So any periodic signal can be expressed in terms of complex exponentials. So the eigenfunction phi kt, a whole range, all series of eigenfunctions that Fourier proposed was of the type e raised to power of j some constant times t, omega naught and any multiple of omega naught times t. All of them are basically eigenfunction. So e raised to power of j omega naught is first eigenfunction, e raised to power of 2 omega naught is the other one, e raised to power of j 3 omega naught. We can have multiple of that. So e raised to power of j omega naught t or e raised to power of j 2 omega naught t. So we can have a whole range of such eigenfunctions. In general, e raised to power of j k omega naught t, all of them are complex exponentials, and these are the eigenfunctions which Fourier gave us, and these are also the Fourier basis functions. The beauty of this thing is that they are also basis functions. Now these eigenfunctions j omega naught t, j 2 omega naught t, j 3 omega naught t, these are harmonically related. Now what does harmonically related means? It means that their frequencies are integral multiple of some basic fundamental frequency omega naught. So fundamental frequency is omega naught, its harmonics are 2 omega naught, 3 omega naught, 4 omega naught with plus or minus, so it is basically multiple of the fundamental frequency. So these are also called the harmonics. So these set of harmonics where we have any value of k starting from 0 plus minus 1 plus going on. So these are basically harmonically related complex exponentials. And we know what is omega naught. Omega naught can be taken, you can say explained as the angular frequency, and it is related to time period by this factor 2 pi over t, as we see right here. And Fourier series, what Fourier proposed was that any periodic signal x of t, at times some books you will see the tilde sign right there. This type of tilde sign is basically used in some books to represent a periodic signal, to differentiate it from non-periodic signal. And in some books they don't actually use it, but in some books they do use this type of a tilde sign at top of this x to represent a periodic signal. So what Fourier proposed was that any periodic signal can be expressed as sum of scaled complex exponentials which are harmonically related. Let me repeat it. The way the Fourier series is defined is that he said that any periodic signal, notice the term periodic. This series he actually proposed was for periodic signal. Any periodic signal can be expressed as, can be represented as, or can be shown as, or can be expressed as sum of scaled complex exponential which are harmonically related. So this that you see right here is the whole definition of your Fourier series. This is what Fourier proposed, that if you have a periodic signal, irrespective of the shape of that signal, if it is periodic, if it repeats after a particular time period t, then you can express that periodic signal as sum of scaled complex exponentials which are harmonically related. And this is the expression, mathematical expression for the same thing. So this is what Fourier proposed, that if you have a periodic signal, then you can express it in terms of harmonically related complex exponentials scaled by some factor. And in your mathematics earlier in FSC also, and maybe some other maths courses that you have already done, you have already been dealing with these Fourier series or expressing periodic signal as Fourier series, computing the coefficient for those Fourier series. So these were things we were already doing. The theory actually that Fourier proposed was, remember that this is valid for a periodic signal. The important point is that it is valid only for periodic signal. And how do we find out the values for these coefficients AK? This is again a simple formula that can be used, and we can find out the values of these coefficient AK. Okay, before I actually venture into there, let me first of all correlate it with what we already know. Okay, so for continuous time, we developed or explained the concept of eigenfunction, and we said that, well, if you have a continuous time system, xt input, yt output, and this is basically a continuous time LTI system, and this LTI throughout this course and throughout will just be sticking to this LTI thing. So if this is any continuous time system with impulse response, if you have something like this, so what eigen concept says is that if you have an eigenfunction, then output would be the same eigenfunction multiplied by its eigenvalue. So this is the whole concept of eigenfunction. And how to identify eigenfunction? One eigenfunction was given to us by Laplace. He said that, well, e raised to power of st is an eigenfunction, and we actually checked and found that yes, e raised to power of st is an eigenfunction, because if we give that as an input, the output comes out to be h of s times e raised to power of st, and we actually showed that this h of s was actually integral minus infinity to infinity h of tau e raised to power of minus s tau d tau. This is actually what Laplace gave us. And this is not one eigenfunction, it's a whole series of eigenfunctions, because this s is basically a complex number, and we can have any complex number here. So it's a whole range of, you can say, eigenfunctions. Keep changing s, keep putting different complex value, you will have a different eigenfunction. But each eigenfunction will have its own eigenvalue, and we can find out the eigenvalue by using this. And this is from mathematics. We have already seen this. This is nothing but Laplace transform of h of t. It is just this. Now, Fourier actually extended the same concept, and he said, well, e raised to power of j omega t is also a eigenfunction, and this omega is some constant, and if you see this and this, it's one and the same thing almost, because this j omega is also a complex number. It is just a purely imaginary complex number. He showed that this e raised to power of j omega t, if you put this, then this is also eigenfunction, and the output here would be, you will see j omega t, the same thing, multiplied by something. And from comparison, if you just see, it is just s being replaced by j omega, s being replaced by j omega, and you will see that you will have something like this. Later on, we will show, I'm just sort of jumping ahead, but later on we will just see this. This is going to be minus infinity to infinity h of tau e raised to power of minus j omega tau d tau. And later on, just a few lectures later, we'll see that this thing is, does anybody know what this thing is? But I'm not going to go there yet. So this is basically very similar to what Laplace gave us. So if you give complex exponential, output is complex exponential into h of s. And if complex exponential, this s, the complex part, is just purely imaginary, then this is what Fourier gave us. By comparison, we can see that it is very similar. These are very similar. So what at times it may look like, well, Fourier sort of copied, and what's the big deal? So it's just replacing s with purely imaginary thing. It's one the same thing. But Fourier gave us much more than this. He talked about this complex exponential e raised to power of j omega t, and he said that, well, if you have any periodic signal, if you have any periodic signal, then you can express that periodic signal x of t in terms of sum of scaled complex exponentials which are harmonically related, e raised to power of j, and this is for k equal to minus infinity to infinity. And we can expand this. If you put let's say k equal to 0, you will end up getting a DC value or DC content a naught, and then we can just plug in value of k equal to 1. This will be a1 e raised to power of j omega naught t, or 1 omega naught t, and then we have a2, the coefficient for e raised to power of j 2 omega naught t, and it will goes on and on and on. And similarly, we can put k equal to minus 1, and it will end up giving you minus j omega naught t. And similarly, a minus 2, and it goes on and on. So this is what actually Fourier gave us in addition, that if you have any periodic signal, then you can express that in terms of sum of scaled complex exponentials which are harmonically related, and it will have some fundamental frequency omega naught, and this omega naught is related to your time period t, the repetition time period, by this relationship 2 pi f naught, or equal to 2 pi over t. And we know that f naught is actually equal to 1 over t. So he actually gave us this additional thing. Now this complex exponential, which is purely imaginary, he showed that this can be used as basis function, or this can be used as building block, or in other words, we can break up periodic signals in terms of these complex exponentials. These complex exponentials, if you just take one complex exponential, it's not a real thing. It has a real part and imaginary part both. But if you take two complex exponential, if let's say a1 and a minus 1 are same, then they will be complex conjugate and you will end up getting something like this. Let's call it b naught plus b1 cosine omega naught t plus b2 cosine 2 omega naught t. Like that it goes on. Two complex exponentials which are conjugate of each other with the same coefficient, we can write it as a sinusoid. So this is something which happens if you have a periodic signal which is a real signal. For real periodic signal, we can say that we can express real periodic signals in terms of sum of scaled. Now here we will have k starting from 0 to infinity bk cosine k omega naught t. So this is for real periodic signal. And real can also be written in shape of these complex exponentials, but you will see that conjugate complex exponentials can be combined and written as single sinusoids right here. So this is the additional thing which Fourier actually gave us, that in addition to giving us your eigenfunction, which is e raised by j omega t, very similar to the Laplace eigenfunction, he actually showed that these complex exponentials are very useful basis function, and these basis functions can be used to build periodic signal. In other words, periodic signal can be broken up in terms of these complex exponentials. And you will notice if we just do it for any real periodic signal, you will notice that these complex exponential occur as conjugate pairs and can be written as sinusoids. So real periodic signals can be expressed in terms of sum of scaled sinusoids. So this is the theory base for Fourier. Okay, so now typically it is expected that students already have done Fourier transform and Fourier series and are already conversant with mathematics and know complex exponentials also. But typically I do go into these details because with experience I know students don't normally have that much depth about these Fourier theory or periodic signals or things like that. Okay, now how to find these coefficients? Once we have Fourier series, then how do we find this if x of t is a periodic signal? Fourier series for that would be given by this thing, minus infinity to infinity ak e raised to power of j k omega naught t. And as I mentioned, if it is real, then the same thing would be bk cosine something. Now another very interesting thing comes out. The interesting thing is that if you plot after Fourier transform, this is not a transform, it's just a Fourier series version, but generally if you have any periodic signal, you will notice that the frequency contents of that periodic signal would be discrete frequency components, which are multiples of some fundamental frequency. So it will have a DC content, it will have your omega naught, it will have 2 omega naught, like that. It will have frequency contents which are multiples of fundamental frequency. And that is true for any periodic signal. Now this is a very important concept. If you have any periodic signal, irrespective of shape and form, let's take any irregular shaped periodic signal. Now as long as that signal is periodic, all we need to know is the time period for that periodic signal. So let's say we had some periodic signal x of t. All we need to know is that what is the time period? What is the time period for that periodic signal? And from that time period, we can find out your fundamental frequency, which will be at 1 over t. We can find out fundamental angular frequency, which will be 2 pi over t. If you want to know the frequency contents which are present inside that x of t, and you do, let's say, take Fourier transform and plot on omega axis, you will notice that it will have frequency contents which are multiples of fundamental frequency. They are going to be multiples of omega naught. In between, it cannot have any other frequency content. For example, if time period for this thing came out to be, let's say, 0.01 seconds, if it is repeating after 0.01 second, then fundamental frequency would be equal to 100 hertz. And so omega naught is basically 2 pi times 100 hertz. This will be your angular frequency. So the frequency content, either we can have omega axis or we can plot on, let's say, f and show what all frequency contents are there. You will see that it will have f naught to f naught. In other words, the frequency content present in this signal would be some DC value and 100 hertz, 200 hertz, 300 hertz. So it cannot have any other frequency content in between. So 100, 200 hertz, 300 hertz. It can have these types of harmonics present, but in between, it will have no other frequency. So if somebody asks, well, what all frequency contents are present in this signal from 0 to 50 hertz, we will say, well, it doesn't have any frequency content there, it just has DC value. So these types of concept is very important, and let me write it here because this is something which we engineers are supposed to know. If you have any periodic signal, then a periodic signal has frequency contents that are multiple of fundamental frequency. Or in other words, the frequency contents are basically just harmonics of fundamental frequency. No other frequency can be present in any periodic signal. So whenever you see a periodic signal, one thing you should be as an engineer very clear. Just see at what time period it is repeating. And whatever time period it is repeating, we just note that time period. Then we find out what are the fundamental frequency. 1 over t gives you the frequency in hertz. And we are absolutely sure, well, the frequency contents present in this signal are just going to be multiple of these fundamental frequency, multiple of 100 hertz. It cannot have any frequency in between. This is a very important concept, and this again is actually an extension of what Fourier actually showed us also, because that periodic signal, if you just express it complex exponentials, it will have complex exponentials that are harmonically related. It cannot have any other complex exponential. So this omega naught multiplied by some constant k. It will have just harmonics of the fundamental frequency. And interestingly, the DC value, DC value that you see, that 0 frequency, is also considered as 0 harmonic. Now, how do we know that a DC is present or not? That is very easy to see. From here, we know that there will be a DC value present, because if you see the mean of this signal, it is above 0. Mean is above 0. That means we have a DC component. And we can just judge seeing. That's one more easy to see sinusoid. If you see a sinusoid which has mean around 0, it has no DC component, and a sinusoid is a single frequency. And if you see a sinusoid whose mean is somewhere here, it is going like this. This is basically the same periodic sinusoid but having a DC value. So adding a DC value just shifts it up. mean value up. Same goes right here. If there was no DC, then the mean value would be lying at 0. So these are small points which are very useful. Excuse me. So these are very useful, important points. And these points will be useful not only in this course, rather more in other courses, not in this course that much. Because now is the time to talk about general property of signals, general, you can say, features of signals. Here we are talking about periodic signal. So we found out one important property of periodic signal, that the frequency contents of periodic signal would be multiple of fundamental frequency. It cannot have any other frequency content. And the fundamental frequency of periodic signal can be found from the repetition time period, T. Just take the reciprocal of that, it will give you F naught. So F naught that you see is here. And omega naught is the angular, you can say, frequency. Angular frequency is linked with frequency by just this 2 pi factor. And typically we always write omega naught in terms of 2 pi into something. So whatever value you see in omega naught, it is conventional to write it as 2 pi multiplied by something, because that something actually is your F naught. It gives us visually the frequency in hertz. And the units for that, I believe you should already know, it's basically radians per second. The unit here is hertz. At times hertz is written as cycles per second, one is the same thing. So some basics about the signals. So what we saw was a few things about Fourier series, concept given by Fourier theory, why is it important, and some properties of periodic signal, which can be seen from Fourier thing also. And very important aspect of periodic signal, that it can have frequency contents which are multiples of fundamental frequency. And even DC is a multiple of fundamental frequency. You can say it is basically the zeroth harmonic. And then we have first harmonic, second, third, fourth, and we can keep going on. So how many harmonics we can have inside any periodic signal? That actually depends on the shape and form that we have for that periodic signal. For example, if you have a simple sinusoid. Now, single sinusoid is basically just one frequency. So you will see that it will have just fundamental frequency, and depending on whether the mean is 0 or not, it may have some DC value, but just fundamental frequency. It will not have higher harmonic, a single sinusoid. And otherwise also we know that we can break it up into two complex exponentials, which are basically conjugate of each other. So K1, K minus 1, that type of thing. And we'll see that, we'll do multiple examples next week, and these things will become even more clear. So this important aspect of periodic signal is that it has frequency contents that are multiple of fundamental frequency, and it cannot have any other frequency contents in between. In between, it cannot have any other frequency content. So same, it can just have multiples of fundamental frequency. How many of these harmonics it has? What are the value for those harmonics? That actually depends on what shape you have for that particular periodic signal. So this was for periodic signal. Now let's continue and talk about the Fourier series itself. In a Fourier series, again, we have coefficients. We have this coefficient AK. So how do we find this AK? To find this AK, you have already seen it in mathematics, but let's just derive a simple formula for that. And this is something you have already done in your maths courses. So the formula that we had for, you can say, Fourier series was basically sum of AK e raised to power of jk omega naught t for k equal to minus infinity to infinity. Now, if we multiply both sides, by e raised to power of minus j n omega naught t, So this is what you will end up having. So we are just multiplying both sides by e raised to power of minus j n omega naught t. And then we integrate both sides within one particular time period from 0 to t. And we take integral from 0 to t dt on both sides. For this product and for this sum of products, we actually take integral of that for the whole range of t from 0 to time period t. So within one time period, we take integral of this. Then if you just see the right hand side, we can take integral inside the summation, and we end up getting this integral from 0 to t e raised to power of j k minus n omega naught. We are just combining these complex exponentials together and written it as j k minus n omega naught. We end up getting this integral that we see right here, which is actually difference between k and n. So now this integral, if we just separately see it, let's see that what we have for this integral. So this integral, if we separately see 0 to t e raised to power of j k minus n omega naught t dt. This complex exponential can be, you can say, written in terms of sinusoid, real part and imaginary part. So we end up getting cosine and j times sine. So we can have integral of both separately. And this integral, if we see, a very interesting thing comes here. If k is equal to n, this thing becomes cosine of 0. K equal to n, this becomes sine of 0. Sine of 0 is 0. So at k equal to n, this imaginary part becomes 0, and cosine of 0 is 1. So at k equal to n, the first part becomes integral 0 to t 1 multiplied by dt plus j times 0. And this integral 0 to t dt ends up giving you value t. And if k is not equal to n, you will have some integral value right here, because k and n are both integers. So if both are not equal, you will have some value here. So it will be cosine of some multiple of omega naught t. So some sinusoid here. And similarly, some sinusoid right here. And that sinusoid has to be integrated over one particular time period. Now we know about sinusoid, whether it is a cosine or a sine. If you have a cosine over one time period, this is what it is going to be over one time period. If it is a sine over at one time period, this is going to be something like this over one time period. So this is from 0 to t. And if you integrate it with respect to t, you will notice that this part area and this part area, because it is equal, the integral will end up giving you 0. Same goes for sine. Sine or cosine integrated over one time period will end up giving you 0. So this is what we end up getting for sine. So this is what we have. This integral will have value equal to t at k equal to n, and at all other values of k it will be 0. Now if you see this integral lies inside this summation, and in this summation we have values of k ranging from minus infinity to infinity. So you have all these ak multiplied by the integral value right here. So as we keep changing the value of k, only at k equal to n does this integral end up giving us value equal to t. And at all other values of k, this integral ends up giving us 0. So this whole summation ends up giving you single value, and that single value will be just a n times t. Once k is equal to n, this becomes a n, and this becomes t. At all other values of k, this whole integral, we have shown it here, is 0. So this right hand side is just a and t, and left hand side is basically this whole integral right here. And that is what we see right here. And from a and t, we just take t on the other side. So a of n will be equal to 1 over t times this integral. And this actually is the formula which actually tells us how to find coefficients a. So an is equal to 1 over t integral over one time period of x of t multiplied by e raised to the power of minus j n omega naught t. So this is basically your formula for computing your an. And we can just keep replacing value of n 0, 1, 2, 3 and accordingly just see that what this integral ends up becoming. Now this periodic signal whose coefficients we are trying to compute and we are integrating it over one time period, it can be easily seen that whether you integrate it from 0 to t or you integrate it from 2 to t, 2t to t to 2t, 3t to 4t. So at any particular single time period interval, we can take this integral and it will give us exactly the same value. So the interval of this integral cannot be just 0 to t. You can take any interval, but it has to be one time period interval, and you will see that it will end up giving us the same result. So at times the same formula, we just write it in this shape. An is equal to 1 over t integrated over one time period x of t e raised to the power of minus j n omega naught t. And this one time period is time period for this periodic signal x of t. Okay. To summarize, if x of t has a Fourier series representation, then the pair of equations that define Fourier series of a periodic continuous time signal are given by this. Your periodic signal can be expressed as sum of complex exponentials harmonically related, and where this omega naught is 2 pi over t. And we can find the value of this coefficient using this integral formula, where you can just replace omega naught by 2 pi over t. So these pair of equations actually completely describes your periodic signal, continuous time periodic signal. So this was talking about this slide set number 7. And in this slide set number 7, actually we talked about the eigenfunction and eigenvalues, and we showed that how we can use these eigenfunctions and eigenvalues to find out output for simple sinusoids or complex exponentials type of input. And then we also talked about your Fourier theory, that what is Fourier theory and how is it important and why it is useful. And we also talked about the you can say implications of Fourier theory as regards periodic signals, because Fourier series specifically deals with periodic signals only. And in periodic signal, we showed that it can have frequency contents which are harmonically related to fundamental frequency. So these were few important concepts that were covered in this slide set. So here's a summary of what we covered in this slide set. We talked about your Fourier basis function, Fourier series, and some detail about Fourier transforms. And we know that they are extremely useful for frequency domain analysis and also for solving differential equations. And we actually showed that e raised to the power of st is an eigenfunction, and we showed that this eigenfunction was actually given to us by Laplace, although it's not mentioned right here, but later on we'll talk about this also. And for this e raised to the power of st, we showed that h of s is the corresponding eigenvalue. So this eigenfunction, the eigenvalue is h of s, and h of s is integral minus infinity to infinity h of tau e raised to the power of minus s tau deta. And this is same as the Laplace transform of h of t. So this is h of s. And then we showed that if we can break up your input signal in terms of eigenfunctions, it becomes very easy to find out output for that particular input signal. And it's very much like the convolution concept we showed earlier, where we can break up your input signal in terms of impulses and we can find out output. We also talked about Fourier basis functions, which are basically set of harmonically related complex exponentials. And we showed that any periodic signal can be represented as infinite sum of Fourier basis functions, where the first harmonic is equal to fundamental frequency, and the other harmonics are basically multiples of that fundamental frequency. And we also derived the formula for computing the coefficients of Fourier series. So this was the summary of what we covered in this. And again, in this slide set, questions 3.1 to 3.5, open and Wilski signal system, you can easily deal with these questions. So this was the lecture, and if there are any questions, please go ahead.